Okay, this is a video recording of my Sustainable Systems project presentation. My name is Ryan Polacheri, and the title of my project is Real-Time Carbon Emissions of Campus Buildings. So here is a picture of some campus buildings, and it's pretty clear that these buildings aren't directly emitting anything, right? So for example, there's not smokestacks on these buildings that are pumping CO2 into the atmosphere. So when we think about a building's carbon emissions, there's nothing we can directly meter or directly observe for these buildings because for example, there's not smokestacks that we can put a sensor on to figure out the CO2 emissions. So how do we calculate the building emissions then? Well, we have to backtrack from the usage of energy resources. So for a given building, a typical building on UIowa's campus, the building's going to be using electric, and it'll be using steam for heating and chilled water for cooling. This is your typical building at UIowa using these three energy resources. And if we want to calculate that building's carbon emissions, we have to attribute the usage of these resources to the carbon emissions that were associated with generating these resources. Okay, so for example, for electric, we have to backtrack the electric usage to its sources. So our source of electric is Mid-American Energy Company, or we generate some electric at natural gas engines. And we also have a solar array on campus. It's not in this diagram, but we get electric from any of these sources, and these sources are what have the carbon emissions. Mid-American Energy Company has the carbon emissions, or these natural gas engines are burning natural gas, and those are what have the carbon emissions. Okay, so we backtrack from an electric usage to the associated emissions. And for heating, well, how do we heat? We heat using steam. Okay, but how do we generate steam? We generate them using boilers at the main power plant. And how do the boilers generate steam? They burn coal, or they burn biomass, or they burn natural gas or plastic or trash or some other fuel, and these fuels are what have the carbon emissions. Okay, so we're able to backtrack the steam usage of a building to the associated carbon emissions. Okay, now another thing to note is we tail off some steam to electric turbines, and these electric turbines are going to contribute to the electric that could go to a building. So we use some steam for electricity generation. This is our co-generated electric, and we use the rest of the steam for heating. Kind of. So our last resource is chilled water. So we generate chilled water in our chilled water plants, and we generate chilled water either by feeding electric into an electric chiller, or this is another place the steam could go. We have steam chillers that use steam to generate chilled water, and so electric has its carbon emissions from these three sources, and steam has its carbon emissions from these sources. So we're able to backtrack chilled water usage back through this diagram to get a carbon emissions value associated with the chilled water usage. So, and this is a bit of a simplification of the UIowa energy system, but the main idea here is we take these energy resources and we backtrack to the source of those resources to get a carbon emissions value for the building. Okay, so what are the metrics we care about? The metrics for this project are, for a building, can you tell me the CO2 emissions per hour? Or if you want to consider that buildings of different sizes are going to be using different amounts of energy resources, you could use a metric like CO2 emissions per a unit of area per hour, right? So that's like kilograms of CO2 per square foot per hour, for example. So these are the metrics we want to calculate, And why do we want to calculate these? Well, this metric enables the ability to optimize for carbon emissions. So the reference here refers to a carbon first approach which declares that like it's more important to consider how much carbon an operation uses and not necessarily how much energy an operation uses. Because if a building, for example, is using a lot of energy, but it's using its energy like very intelligently, and considering the fuel mix of its energy resources, then, for example, it could use a lot of energy but not emit a lot of carbon. So that's the carbon first approach, and essentially the metric empowers us to optimize for carbon emissions rather than for energy efficiency or cost or some other metric. Okay. And another thing I like about this metric is it has more meaning to the general public, I think. So, for example, if we say a building uses 2 MMBTUs of steam, a lot of people are not going to really know what 2 MMBTUs of steam is, like, or what that looks like. But if we say it used, 100 kilograms of CO2, people know what CO2 is. They know it's not good. So it has more meaning to the general public. And furthermore, if you convert your CO2 value to like something like gasoline equivalent, it'll make more sense to the general public. So instead of saying it used 100 kilograms of CO2, say it emitted 10 gallons of gasoline worth of CO2. Okay, so I think those values generally have more meaning to the general public. Okay. So how do we do this backtracking of energy resource usage to carbon emissions? Well, we have data. So all those arrows I showed in that diagram, there's data that tells us all the amount. There's data that tells us each part of the process. Okay, so there's between 50 and 100 data sources, and for example, these data sources will tell us how much coal is being shoveled into boilers, or how much steam is getting tailed off and routed to electric turbines. So we have data that represents each part of the process, and I haven't counted, but there's between 50 and 100 different data sources to backtrack from energy resource usage to emissions. And of course, this data needs to be retrieved and calculations performed in real time in order to get that real-time carbon emissions value. And to do this, I built custom software to ingest all data sources, perform necessary calculations, and to display the final emissions results. So I'm going to demo that software, but first I have some project sponsors to acknowledge. So these sponsors sponsored the project not with money, but with their time and with their expertise. So the first project sponsor is George Patterson. He was the data expert for this project, so he's the one who knew like all the different data sources that would be relevant to this calculation and where I could find them and all that. So without George, I would have been completely lost in collecting all the necessary data to perform this calculation. And our second project sponsor is Melissa Gill-Martin. She was the emissions expert for this project. So, for example, the data we have is how much coal is going into the boiler or how much natural gas is going into a boiler. But what needs to be done is those values need to be converted into CO2 in order to get a value of CO2 emissions. So Melissa consulted on those emissions factors to convert fuel inputs to carbon emissions. So she corrected more than one of my emissions calculations. So really contributed to the final result of that CO2 value for a building. Okay, so now I'm going to demo the software. Here is the software, and there's a lot of buttons here, but the button we care about is the building emissions report. And with the building emissions report, I guess the first thing to note is start date and end date. So you can pick any start date and end date within reason, but I'm just going to pick like this week. So 5/2 to today, and we will get hourly emissions for the buildings we select. And the buildings I have selected are McLean Hall, the main library, and the Papa John Pavilion. So we're going to look at these 3 buildings, and we also have a grid strategy. So there's 2 grid strategies here, and there's pros and cons to each of these strategies. But I'm going to go with the Mid-American Energy grid strategy, and we're going to generate an Excel, and then we're going to generate the dashboard. And the dashboard is going to show carbon emissions in that gasoline equivalent value, the value intended for the general public to understand carbon footprint at a glance. Okay, so let's execute this, and it'll take a minute to get all this data and perform this calculation, but just imagine all the things it's doing right now. It's pulling all that process data for how much fuel is going into boilers and how much electric we're purchasing from Mid-American versus how much is coming from co-generated electric. And so it's pulling all the data necessary to backtrack emissions from the building's energy usage. And it's going to produce this data on an hourly basis. So we could have done like by minute or by second or by day, but an hour just seemed like the best unit to start with. So here we go. This is our real-time value. So McLean Hall today from 2 p.m. to 2:59 p.m. used 55 gasoline gallons worth of CO2. So to be clear, this is CO2 equivalent, not energy content equivalent. So if you lit 55 gallons of gasoline on fire, the amount of CO2 that would be emitted from that is what this value is saying. And if you flip, you got some more energy stats on the back side. So you can get values like CO2 per square foot and all that. That's all on here as well. But this is like at a glance, like what is the carbon footprint for this hour? And these all have stats as well. And of course, you see the breakdown of how much gasoline was for electric and steam or chilled water. And you can go back right to that anywhere in that time frame we selected, and you can see the value changes as I go back. So if we go back. I can go back to May 2nd here, and we can see the emissions at that time from 12 a.m. to 12:59 p.m. So let's look at another building. Let's look at the Papa John Pavilion. Oh my gosh, look at that. 2,787 gasoline gallons worth of CO2. So quite a lot more than little old McLean Hall. And you can see most of it is from this chilled water usage. Like it's using 2,651 gasoline gallons worth of CO2 just for the chilled water. So that's kind of an interesting thing to see there. And let's look at the main library. So you'll see the main library is somewhat close in terms of square feet. So some Papa John Pavilion is 642,000 square feet. The main library is 468,000 square feet. So they're somewhat similar in square feet, but the main library's got its chilled water usage under control here, or at least more so. So you can see it's only using 158 gasoline gallons in the same time frame. And we can go forward on this value as well, anywhere in the time frame. So that's a demo of the software. And we got 2 more slides to wrap up this presentation. So with this this software platform in place, we're in a position to perform experimental results on this CO2 metric. So I put together 2 pretty simple experiments. And the first experiment was looking at a constant hourly usage. So imagine this is like some contrived building that uses the same amount of each energy resource every hour. So this building is going to use 100 kilowatt hours of electric, 1 MMBTU of steam, and 500 gallons of chilled water. And it'll use this every hour. It won't change. And given this workload here, we can look at the emissions that resulted from this workflow throughout time. And so here's a graph of that. And our time frame is every hour from 12/16/2022 to 5/5/2022. And given this workload, how many emissions did this workload result in? And you can see there's two big spikes here. And this first spike, I looked into it a little bit. That was January 14th, 2022, from 10 a.m. to 11 a.m. Huge spike in carbon emissions for this workload. And the reason for that spike, what I was able to see is the amount of chilled water that we were producing dropped 5,000 gallons. So we were still spending all the fuel inputs to produce chilled water, but the amount we were actually producing dropped by 5,000 gallons. So, you could take your guesses into why that was. Like, maybe there was a water pipe that was down for maintenance, and we had to turn it off and fix it. Or maybe it's just bad data. Maybe a sensor went out, or a sensor needed to be recalibrated. So the data we were collecting in this time frame was off. But nonetheless, we can see that something happened here that caused a huge spike in carbon emissions for this workload. Okay. And the second experiment was looking at an actual building on campus and tracking that over time. So this was McLean Hall, and of course, as any building would, as would be the case for any building, its energy resource usage is going to rise and fall for each of these items over time. It's not going to be constant like this workload. So this is a real building over the same time frame, looking at its CO2 emissions. And you can see like it's mostly pretty low, but then we start spiking here towards the end of the time frame. And this big spike here was on 4/29/2022, where the chilled water usage of McLean Hall jumped over 6,000 gallons of chilled water. So it went from 3,000 gallons of chilled water to 9,000 in that time frame. And that's what resulted in this huge increase in CO2 emissions. Okay. So those are two experiments, pretty simple experiments, but just demonstrating that you can use this platform for experimental results. Okay, last slide here is future work and limitations of the solution as of now. So one item of future work is to actually deploy this software in buildings, in a kiosk that's in the building that people live and work at. So imagine you walk into McLean Hall and you see, like in a kiosk, like the carbon footprint or the gasoline gallons that McLean Hall is emitting in real time on that dashboard at the kiosk. So the reason to do that is, first of all, just to raise awareness. Like, if people understand like the carbon footprint of the building that they live and work in, like they'll be more aware of the issue. And second, it might actually influence their behavior. So for example, McLean Hall, as far as I know, doesn't have automated lights that turn off when there hasn't been any motion for a while. So there's no automated lights that turn off. So if people are seeing the carbon footprint in real time, maybe they'll be more aware, and they'll remember to turn the lights off themselves. So the next item is to improve electric grid data. So I showed that little flipper with two different grid strategies, and there were pros and cons to each, but there's still room for improvement. and in the area of calculating carbon emissions of electric from the grid. We're kind of limited in the amount of data we have that's publicly available for grid emissions when you compare it to what we have for our power plant. For our power plant, we have very, very detailed data, and we can be pretty confident in our value for carbon emissions. But for electric grid data, it's just not the same type. So it's just not the same. So if we could improve that data somehow, that'd be great. Incorporate natural gas usage. So most buildings on campus use steam for heating, but some of them use natural gas for heating if they're too far away from the central steam system. Or some buildings have natural gas for other reasons. For example, the chemistry building has a natural gas line because they use Bunsen burners and such in the chemistry building. So if we could incorporate natural gas usage for the buildings where that applies, that would allow us to calculate emissions for those edge case buildings. This would be really cool if we could direct intelligent process decisions based on our carbon emissions value. So again, this is like if we have to do some energy intensive process, can we wait to do that process for when our carbon emissions factors are low, like when we're producing the least amount of carbon and our fuel mix is most ideal for minimizing carbon. So if we could direct our high energy processes and have them wait for low carbon times, like that would be really cool. And the last item I have here is like using what if analysis with this system. So for example, other groups in this class built models that assessed how much carbon building a solar farm, for example, on campus would save. Like, what if we could plug that into the software model and get real-time savings if we installed a solar farm? Maybe another example is like if we took out a boiler at the power plant and instead built a concentrated solar thermal plant, how much carbon would that save us at the end of the day on a real-time basis? So that's the what-if analysis. Gives us a means to assess these models that could improve the carbon footprint of campus buildings. If you want to get really fancy with it, possibly you could do machine learning as well, where you say, like, given a set of models and given a certain amount of budget, what set of models is going to reduce the carbon emissions of campus the most? So there's a lot that can be done here with this what-if analysis when you have this kind of system in place. Okay, so that's the end of the presentation.